So our next speaker, it's Nathan DeBardeleben from Los Alamos National Lab. Nathan has been on the heroic years of Multicore World in 2017 when we were in Wellington and we were getting there, and has been a supporter since then, and finally got to come back all the way from Los Alamos. Thank you very much.
Thanks, Nicholas. Hey, folks. Yeah, so as Nicholas said, this is my second time here. But last time I was here, I was actually presenting on a completely different topic. I used to lead LANL's efforts related to cosmic radiation-induced errors in supercomputers. So I was here talking about reliability and resiliency. That is, Department of Energy decided around that time, or a little bit after that time, that we would just stop buying computers that didn't work, and just enforce that our vendors had to provide us reliable computing. And hopefully you recognize how silly a statement that is, but we've stopped largely investing in reliability and fault tolerance studies, though we have heard a little bit about them, of course, across this week. So I then started leading a team related to manufacturing machine learning at Los Alamos, and it was very applied machine learning on important data sets. And since then, in the last 2 years, I took over co-leading. We started a major project that I'll be talking about today called ArtIMis. It's our AI for mission, LANL investment, and I'll be talking about that over the course of the day. The talk is going to be a lot higher level than perhaps some of the other talks you've heard this week. There's a lot to cover in this, and I'm just going to skirt the surface of it to give you an idea. Every one of the topics in here could have deep dives in it. We've got about 120 employees working on this project for 2 years, so I'm not going to be able to do justice to that in 30 minutes, right? So I'll just give you a taste of some of the stuff that we're doing in this effort. So one thing you might obviously ask, and perhaps this isn't necessary in an audience like this, but why would you focus on AI given the efforts that's going on in industry, right? And I think we sort of believe that industry has led the way in AI for science, believe it or not, but it's unlikely to lead a sustained effort in this space. And so if you studied this area, you'll know that a lot of these foundation models that have come out of, or really surrogate models that have come out of industry, have been abandoned. And that's not surprising. It's not an insult against the industries focused on those areas. But things like Aurora and Climax, both really grounding technologies that have really influenced a lot of work in this space, were abandoned. DeepMind, you might have heard DeepMind had some really cool analysis of interesting materials that should be studied, that they were very proud of, and then Lawrence Berkeley Lab looked at them and found them all to be not particularly interesting. And so you need this connection deeply in with a academic effort that can take care of it. And so that's one of the things that we've really been focusing on in our effort here. So DOE, the Department of Energy, has invested significant effort in developing an AI strategy over the last couple of years. We move pretty slowly. That's probably not a surprise to anyone. So we write lots of documents about how we would address this if we were to get funding. So I was co-author of several of these docs. I'm sure folks in the audience were as well. We worked on these for years. Secretary Wright is our current Secretary of Energy for the Department of Energy. And he came to Los Alamos and announced what at the time was going to be called Manhattan Project 2.0. That was after we were preparing for something that was called FAST during the last administration, and has since morphed into AI Manhattan Project, and now finally the Genesis Mission Project. We've heard Genesis mentioned several times this week. What you'll hear today from me on ArtIMis is essentially a feeder project into Genesis that we had prepared in Los Alamos initially. So I'm going to spend a little bit of time on this slide to give you kind of an overview of what we're doing in ArtIMis. Again, I mentioned it's about 80 to 120 staff over 2 years. For LANL, that's a pretty major investment. I know it's not from an industry perspective, but what we did is this is not funded through like NSF, if you're wondering about that kind of thing. It's not even Department of Energy base funded. What the lab does is they pull off sort of, if you will, tax money. If you're familiar with LDRD, all the labs have this. We pulled off that, and then we competed for the largest LDRD ever. To my understanding, the largest one in DOE history. So it's a $20 million a year LDRD investment. And so we had this belief that we really needed to have a sustained effort of a lot of staff coming together, working closely on projects, not little individual PIs doing awesome research, but a really sustained effort because we felt that that was really necessary. The lab got behind us and is invested in this, and we're still going strong on this. So each of these efforts here are sub-teams from ArtIMis. So our goal is really to develop an ecosystem of agents, AI agents, and foundation models. We'll talk about those two things in this talk to address DOE mission needs. You've heard a lot about agents over the course of the week. I'll show you what those look like from our perspective. We essentially have this broken up into two groupings of teams. There's an application areas subset of teams and enabling technologies. In our application areas, we have multi-physics, multi-materials. That's sort of classic Los Alamos bread and butter work. We also have material discovery and material fracture. You saw a little bit from Emily yesterday about material fracture. I'll show you a little bit more of that as well today. And then we have a group that's about ligand discovery related to cancer treatment and some other things important for LANL. Last year, we shed off two groups that were related to biology as well as energy grid optimization efforts. We kicked those ones out after we had had an initial round and moved on from those. And we have an sort of what I'll generally call like a CS-focused efforts down here in our enabling technologies. You heard a little bit from Emily yesterday about test and evaluation. We have a foundation models group, design, discovery, and control group, which is where our agentic work lives, and then a data group. So I think of these as like our CS nerds, and these as our application domain people. And so CS people from foundation models are bleeding into these other teams to help them on the application domains and efforts. There's aspects of this that gets into the real world with robotics and stuff, and I'll discuss that on some of the later talks. As I mentioned, Emily already talked with you a little bit about this yesterday, so I won't spend time on this today on the test and evaluation. And believe it or not, our data effort led to the lab deciding that it was bigger than ArtIMis, and they pulled it off into a lab-wide effort that started on its own now. It's an effort about $10 to $12 million, I think, now, that is to support different data efforts around the laboratory. So we've built several special purpose foundation models, and I think it's worth taking a moment here to talk for a second. I won't be talking at all about, so foundation models maybe in your mind is you're thinking ChatGPT, Llama, and stuff like that. These are non-language foundation models. Our team is doing nothing except for using language foundation models in clear spaces. These are not fine-tuned models on science technology, science papers and things of that nature. We have efforts like that at the lab. I'm involved in some of those efforts. That's not really in ArtIMis, and we're not going to be talking about this today. These are sort of spatiotemporal, autoregressive surrogate models that are pre-trained on next frame prediction. We saw examples of this yesterday from like Karen and some of the other speakers as well. And they're fine-tuned for specific tasks that are important to us, such as downstream tasks. If that doesn't resonate with you, it's very similar to the idea of the way language models are trained. They're pre-trained on next word prediction. You'll often hear that kind of laughed about how it's nothing more than a next word predictor or next token predictor, but then they're fine-tuned for specific tasks. That's what we're doing in this space as well. All of our stuff is open. The intention is to put all of this open source. Much of it is open sourced already. Our things are on Hugging Face with pre-trained models you can just download and try out. A lot of our data sets are fully available online, and the agentic framework I'll show you later is fully open source. We're getting about 2,000 downloads a week for that particular framework. It's our approach. There's many other approaches out there. It's definitely feeding into the Genesis mission work, and hopefully I'll get a chance to show you some of that as well. So what I'm trying to say is, not trying to claim ownership or that this is the right way to do things. It's just our way of doing things, and you're welcome to try it out for yourself. One One thing I mentioned already, that most of our models are trained on autoregressive rollouts. We do a lot of multimodal work, right? So this is not just image, if you will, data sets that are trained for autoregressive, but we also pull in things like the input decks. We call them decks in Los Alamos. Think of input text files. Even equations go into these things for our model building. And they're fine-tuned on new data sets across domain. This is really important to us. We're doing a lot of exploration on how useful this is. So you train on one type of physics and you fine-tune on another. How well does that work? So we have a lot of trying to figure out aspects of what inherent physics properties are being baked into these models and quantify that. Again, you saw some examples from Emily yesterday about how one might think about quantifying that. We work pretty closely with a couple of vendors. This Finding Physics is a reference to a product from NVIDIA called Physics Nemo. They name a lot of their projects Nemo related. And so we have sort of help. We're working with them on an adaptation of that for applications related to Los Alamos. We're exploring a lot of different technologies. If that's important for you to know, I'm not saying transformers are the right necessarily approach. We're also exploring GPT-like discrete tokens across data sets, as well as UNet-based approaches. We have a lot of different competing approaches we're exploring in this space. It's just some of the things we're working on. And then we fine-tune them for specific scalar outputs, time to fracture, physics, numerical quantities of interest, things like that. These are really what you would call true foundation models, and I'm not saying that because I want to think you either think I'm cool or that we're special. What I'm saying is a lot of people will call surrogate models foundation models. That's the pre-trained portion only, which are on the autoregressive rollouts. When you fine-tune them for downstream tasks, it really brings them into the foundation model space. And so we have a lot of things in that space. Let's give you some examples of what these things look like. This is just one of our models. It's called Morph. Up here, it's on Hugging Face. You can get it. It's pre-trained. We have small, tiny ones, and we have monster ones. The tiny ones are good enough for your laptop. Results aren't great, but they certainly will work. And then the huge ones require lots of GPUs to train. And if I remember correctly, the biggest Morph takes about 16 hours to run one epoch on about a dozen GPUs right now. So it's pretty slow moving to train some of these. So you have to sort of adapt to that. What you're looking at here is initial frame of a particular data set, and then a target. This is the real data from a simulation, the second column here. I'm going to show this kind of thing a couple times in the talk. So initial target from a simulation, and then this would be our prediction from it. And you can see a lot of the properties Emily talked about yesterday, right? So kind of a blurring in here, not the sharp sharp lines here. But it does a pretty good job of predicting this. And this is on pre-training on data sets from the internet that are like open data sets. You can get like PDE Bench, PDE Arena, The Well. If you're in this space, you might have heard of those. They're big data sets. And then we fine-tune them the rest of the way on data sets that are important to us. As Karen mentioned yesterday, these kinds of simulations are very costly. And so you have this worry that you need this massive data sets out there. I kind of disagree a little bit with what Karen was saying in that you have to have massive data that is relevant to your domain. We seem to be having a lot of success on taking massive data that's publicly available and then fine-tuning it on a smaller amount of data that's inside of your domain. Example of a fine-tuning of this. So this is Morph again over here. This is on a public data set related to inertial confinement fusion that Livermore released. You can use Morph to predict downstream images like we're doing here, but you also can take off the ends essentially of it. It's like modifying the neurons in the output and then have them predict numerical quantities. And so this particular data set not only has images as output, but then also numerical quantities that they're looking for here. And so we're showing 4 of them here, parameter 1, 2, and 4. And as I'm sure you know, you're trying to get a strong signal across the diagonal here. And this is Morph pre-trained on data that you can get yourself, and then fine-tuned the rest of the way on this small amount of data, which actually you also can get yourself. This JAG data set from right up there, from Livermore, is on GitHub. So I want to give you guys an idea of the way this kind of thing works. One thing you can do with this is of course just a cartoon, is you can take these surrogate models inside of here and then use things like an explorer, we'll call it, or sliders to explore the parameter space of this. Imagine every one of these, as the numbers are on the right here, these are 3 different inputs into a simulation code. Now, our scientists do this, right? So but of course, they're not using a surrogate model for this. These are individual invocations of perhaps a long-running code, like Karen was mentioning, that's very costly for them, produces them one output that then they have to study. And so they do these massive parameter sweeps over, with Python scripts and Bash scripts and whatnot, and then write all this code to glean over these data sets to see if they can find the things they're looking for. Not surprisingly, if you could build a surrogate model like this and then sort of call into it, this is actually one of our surrogate models. It's just a simple example, though. You can get real-time responses like this. Now, again, I'm not going to argue that you would use this to make decisions about what to build or what to fire or whatnot, but instead you use this to downsample what experiments you want to go conduct, perhaps on the right, using the expensive models. This already works for us, and we've also connected this to our agentic framework, right? And so this has just popped a layer up. Now, our agents don't actually control the sliders and stuff like that. That kind of technology exists, but you wouldn't interface a computer to a computer in that way. Instead, what our agents do is they call into the foundation model with these inputs, they get their results back, and they drive it towards a goal that the users asked for. Perhaps, if you were to go back a couple slides on this one, perhaps maybe you want a long jet here. And so we describe things like in that kind of pattern, or you want a long amount of time to fracture. And so we describe them in those ways, and the agents control them and push them towards that direction. And so the human is just sort of pulled up a layer from actually controlling this themselves. So what we've been doing, I'll talk a little about agents on this slide here. What we've been doing is building an agentic design and discovery system driven by industry reasoning models. I will comment that at this point, that what we're doing is we're using the frontier models from industry, particularly Claude 4.7 and GPT 5.2 these days. We've been doing this since GPT 01 at least, and before. We are paying for tokens. We have expensive contracts with OpenAI and AWS and stuff like that. And they actually don't really, the stuff doesn't really cost that much. But I run these things sort of 8 to 16 tasks at a time, running it all the time. And it's really not more than a couple $100 a week of tokens we're burning on this kind of thing. We're doing a lot of predictions of what this might look like in Genesis, how many tokens, how much money we need to spend on this. But my point here is that by far the quality results we get are from the high-end reasoning models. If you take some of the technology I'll show you today, which is again open source, and put it with a crappy LLM and get crappy results, and say, I don't know what this Nathan guy was talking about, these results are awful. Your conclusion should not be that I was wrong. It should be that you chose a crap model. And you could maybe pay a little money and use some of the better models. The other models are not that far behind. It won't be long before those have caught up. But for right now, we get way, way better results. I don't mean like from a thinking perspective, like it's wiser. I mean it's your ability to control it and keep it on task. In particular, in a framework like this where you're controlling it agentically, what I mean is your ability, or our ability, to make it respond in ways that we can then take action on. And so you have to sort of force these things to use tools to respond in structured JSON that you can pick up and trust the results are there, that you can act on. And a lot of times you'll get stuff like out of Llama that you're in the middle of a run and then suddenly its response, instead of responding with structured JSON, I've literally seen this, it just comes back and says, don't ask me to do your homework. Like that's like literally a response that's coming back that we're expecting structured JSON coming back out of it. And so you really need some of these better models in this space. Not surprisingly, this stuff requires inputs such as data, public and private documents, and source code perhaps you want to feed into it. We have this notion of a thinking agents cycle where we have hypothesis and critiquing agents that go through and critique the hypothesis until it is acceptable, then a planning agent writes a plan for how we're going to carry this out. That's a structured JSON. I'll show you what that kind of looks like on the coming slides. And that thing then hands it off to tasking agents. This is a handful of our tasking agents. This is the kind of stuff that you'd sort of, in your brain, we started this kind of before Claude Code was out. I'm not saying this is better than Claude Code. Maybe you should just use Claude Code instead. But a lot of this kind of stuff was sort of before that era. We have the ability to control your computer, run commands in your machine, write code, run code. That probably makes a lot of sense to you today. It probably wouldn't have made sense to you 6 months ago. We've been doing this for about a year and a half. And then, as I mentioned on the previous slides, we then connect in with our foundation models like Transparent Earth, Keelotron, and some of our other models right there. And so the planning agent will sort of plan out how it needs to carry out this. You can search the web, you can go through online databases and things like that. And I should have started with this, find a new alloy that resists fracture at low temperatures, test it in a desired configuration, and maximize time to failure. So we're sort of popping the user up a level so they can control things at that level. Here's an example of one of our projects from the ligand discovery group. Find a ligand that could become a cancer drug, right? And so this is a collaboration with NVIDIA. This project is called Keelotron over here. It's connected in with the Nemotron naming from NVIDIA. We use Nemotron here. We use one of their language models here called Super 49B. It's actually based on Llama, but fine-tuned. It's pretty good for this. We'll probably replace it with one of the frontier models pretty soon. It goes into a generative AI project from NVIDIA called GenMol for GenMolecule. This generates smile strings. They're text strings. Actually, I have a slide on what these look like in a couple of slides. But these are text strings that describe molecules. Then those go into a large simulation framework that we wrote called Architecture here that runs in a supercomputer, calculates the results we're looking for, updates the hypothesis, and around this goes. And this has been pretty successful so far. We've pulled out a handful of promising molecules for a couple of different projects, and those are under evaluation right now. I'll comment that that's a little bit different, perhaps, than I was arguing earlier with like DeepMind, right? So they had the ability to find what they thought was interesting, but not the ability to test it. And that's where I think you need these institutions like national labs or universities that can do the whole cycle. I didn't bring with me the movie for the robotics, but this is what our robot looks like. We have, in the materials discovery effort, we have materials foundation models that have been trained on to have particular material properties that we're looking for. We've got this connected straight in with the robot arm. This robot then takes draws out of that about materials that it wants to try. It actually gets the material elements and melts them in what's called an arc melter. And then it forms that into a shape called a dog bone. Is this a video down here? Yeah, it's a video down there, tiny little. Yeah, it's hard to see. This bottom right. It's pretty slow moving. This is being ripped apart here. This dog bone here. It'll break real rapidly here in a moment. So it forms this into a dog bone in a vacuum, and then puts the dog bone into the stress test, rips it apart, takes video of it the whole way. That video then feeds back. There's a lot of AI in that as well, picking up where the material ripped and calculating things like stress and strain, and then that feeds all the way back in a full loop into the model, updates the model with some new results, and then new data, a new one to try out is pulled out of this. This full loop fully works right now. We have a patent on it on this team. The loop takes about 30 minutes to run one sample, kind of slow. So I think we've bought 6 of them right now. We're going to run 6 at a time. And of course, we're looking for ways to speed that up as well. Emily showed you a version of this slide yesterday. I'll comment on some different things on this slide. She was talking about the testing evaluation. I'll talk a little bit more about the sort of material science behind it. This is from our materials fracture team. So what's cool about this stuff is that, again, these simulations are very costly to run, these ones over here. But what we've found is that we can actually train on these sort of cartoonish examples that are shown here. These are literally what these look like. Emily showed you these yesterday. And they're looking for growth patterns that happen from very simple, it's very simple to generate this, very simple to simulate that. Once it's pre-trained on this, we then fine-tune on the expensive stuff, and we get really good results on that. So one of the ways to evaluate that would be perhaps over here. So this is with 15,000 sims, the foundation model gives lower RMSE and more visually correct pattern than training from scratch. And so what I mean by that is rather than just training from the high fidelity, expensive simulations, instead if you pre-train on these kind of results and then fine-tune on your more expensive results, we get really, really good results from that. That's kind of we found that people sort of have a hard time with that, and I will kind of try to anthropomorphize that for a moment. I think it's not dissimilar from saying something like, training someone on basics of math and algebra and whatnot, and then eventually bringing them into learning about calculus. You could, in theory, just teach someone that has never learned any aspects of math, calculus from the start. Maybe it's harder, maybe it takes a lot longer. So that's the more training samples, but maybe you can get them there. This is like that. We've seen this in a lot of other spaces, and particularly in machine learning too, where you train on things like dogs and cat images, and it picks up basic arcs and circles and whatnot, and then you fine-tune it on your industry's particular advantages. This is one of my only technical slides. In case you're working in this space, I wanted to give you a couple of highlights of some things that we found useful to really get good results. Curriculum learning, where the tasks get progressively harder. Scheduled sampling, where we sample from either the ground truth as well as the rollout. Some pretty cool techniques. This technique seems to only be called the push-forward technique. It's from a paper from Max Welling's group. We've used that and have done really well. Data augmentation, like adding noise. People that work in ML, that won't be a surprise to them that's useful. And then domain-relevant loss functions, like Emily was sort of talking about yesterday. What that looks like is like this. And so so I got two sets of movies here. The left one is before sort of we do those kinds of optimizations, and the right one is after that. And in each one, your left one is the ground truth from your simulation data. This is the costly simulation data, the same one from the left here and the left there. The middle one is the prediction from the ML model, two different ML models before and after. And the right is what's called a residual or a difference. It's nothing more than a subtraction of the two of them. Now, we'll comment, these are autoregressive. So what that means is we only start from the first frame of this. We predict the next frame, and the value of that is used to predict the next frame. So these very easily get off track, right? They sort of have the butterfly effect, right? So you have a little bit of an error, and it starts to magnify and go crazy. And that's what's sort of shown here, right? It's not coming up great here, but you can sort of see the amount of errors that appear in these over here. When we do this improvement, we get a much better results on the right. Now, we've spent a lot of time making this as good as we can get it. I'm not positive that's the right approach. I don't think we should keep chasing this over here and saying, yeah, there's still some errors. Make it better, make it better, make it better. Because our goal really isn't to replace our simulation codes with this. Our goal is to inform design down the line. And also when you pre-train on this kind of data and then fine-tune for some of those numerical quantities, remember back to that ICF example where I was showing you predictions of a couple of those numerical quantities. Often that's really what our scientists are interested in. And when we do that, driving this error down as low as possible isn't actually the goal there. So these have been very useful in this space. We have a really deep collaboration with the University of Michigan and a couple of other universities. This was an example where with Michigan, we pre-trained, they have a model that's pre-trained on about 50 billion molecules, and then we fine-tuned it on, 86 million molecules that are related to some high entropy alloys that are a little harder for us to share in a public space. But we get really good results. You're looking for strong signals across the diagonal here from this foundation model making predictions. This is related to detonation velocity and detonation pressure of a particular project we are working on with them. So I've got a couple of slides on some of our agentic frameworks sort of demonstrating it. It's hard to show these kinds of things. They're, as you'd imagine, they're long running. They're often not particularly attractive because it's a lot of text windows and whatnot over here. But this is an example. What we did is we basically gave our agentic framework, it's called URSA. You'll see a slide on it in a moment. Excuse me. Access to some papers. We told it to go read these papers on the internet that we were interested in, and we told it it had access to a one-dimensional ICF simulation code called Helios. We wouldn't really run the one-dimensional one, but Helios can run in about 30 minutes per invocation. And we told it it needs to figure out how to write inputs to that and evaluate the outputs for it. And so it starts writing and running code. In the full movie of this, which actually is on YouTube, you can watch it. Obviously a little hard to see this kind of text, but you can see it trying different parameters, evaluating where there's getting good and bad results, commenting on why it thinks those values might be good or might be bad, or why it got a bad result out of it. So it actually has reasoning text we're told to print out. And then in a movie form, this neutron yield gets driven up as it runs more and more simulations, and it's exploring different spaces over here to make sure it's confident in this space. Again, from a human prompt. Like, I didn't write any code past the agentic framework. This is where this technology is going, okay? It's a lot more powerful than just buying something on Walmart agentically. This stuff is really empowering some of our staff. This is what the planner looks like. For what it's worth, you get everything. So just to be clear, it's not a total black box. Any of the code it generates, any of the plan it generates, any of the files it generates, they're all yours. They're just in a directory. We often find that the projects do about 95% of the work, and then we go back into a almost functioning project and write one piece of code to fix it, the very last bit across the finish line, let's say. I think of this sort of as akin to working with students. You gave a project, maybe it didn't do a great job, but it did a really good job, and you don't have to do any work. Cost you maybe $10 to run this thing for an hour and a half, and I can run tons of them. And then it becomes a question of how quickly I can evaluate these results. So if you push them into spaces where you don't have verifiers, such as write me a persuasive argument or a persuasive, report, it's very hard to evaluate that. If you push them into spaces where you can programmatically evaluate it, you get really good results. And so our planner does things like it defines the success criteria, it says whether or not code will be required and whatnot, and then these get passed on to our tasking agents, which figure out how to pick that up and execute these tasks. Here's an example of what this kind of looks like. This is connecting in with the MIST model from Michigan I showed it a couple slides ago. This is a kind of silly example, but I want to show you how how high level this is. This literally says, use your vast knowledge of chemistry to generate new energetic materials and smiles. Obviously, a more informed person that actually worked in this space could provide a wiser prompt here. For each of these, use the model, which is this other foundation model. Remember, we're going to call into these models to make a prediction, pull out the values of velocity of detonation and pressure detonation. And density, say the results in CSV, make me plots, things like that. And these are actual smile strings that come out of it. And I told it to plot Pareto fronts. So to be clear, I didn't write the code for this plot. I didn't generate any of these over here. And all I wrote was this text over here. Imagine this powered by scientists that actually knew their space, not a computer guy over here writing this. This takes about an hour to run as it explores all this. Obviously, that's based on how long it takes for those to run. So you can get URSA. It's on public GitHub, totally free, obviously. We have tons of people using it, lots of commits, and it's as easy to install as a pip install with just one line, or you can use it with UV as well. And you can try it out. We have command line versions of it. We also have automated versions that run for long periods of time, so you can sort of interface with it like ChatGPT, if you like that kind of thing, or if you want to turn it loose on long-running examples that run for hours, we've got examples in there for that as well. To give you an idea of how sort of powerful this kind of technology is, People were complaining that we didn't have a web interface for this because we're computer nerds and we're just hanging out in glorified terminals for this. And then so one of our leads of this project while watching the Super Bowl had Ursa write its own web interface. We're using that web interface now. So, I mean, this stuff has really come a long way. If you don't recognize that, you might want to think deeper about like what your experience is, and because this stuff is really quite powerful right now. I also recently wrote an agent for Ursa using Ursa that I needed. So I had a new agent that I needed, and I used the tool to build it, including all of the unit tests, documentations, examples, and whatnot for that. These are some of the universities we've been working with. I've already mentioned University of Michigan. We also have a design, discovery, and control sort of optimization effort with Georgia Tech, and a lot of work going on with the University of California, which is probably not a surprise coming out since we're a UC lab historically. We have a lot of industry partnerships. I'm drawing attention mainly to NVIDIA and OpenAI here. So I've already talked about NVIDIA a couple of times. I will note that in the OpenAI space, we have the only installation, I believe this to still be true, the only installation on premise of an OpenAI model that's their private weights, not the ones they open sourced. So we worked very closely with OpenAI. They brought their weights, obviously under guards, to our guards, transferred them over to us, and these are running on our classified network, which allows us to deal with asking some questions that are not the kind that we release out in the wild. So this is a very fun model to work with in this space, and we work very deeply and closely with OpenAI on this. We have cleared employees from OpenAI working with us on this project. This is just a little fun slide at the very end here. I want to comment. You see a lot of this stuff and, probably on your feeds or whatever social media you've got out there. This stuff's cool. Like, I'm a nerd like you guys. I like this stuff. But I will comment, we don't need this stuff on the right here for this to be useful. This is working all around the world. And I'm going to argue that this kind of stuff is what we already have today. And I often find people say, you can't use this agentic framework stuff until you get artificial general intelligence. I do not believe that at all. We're already working. I don't need these things to be positing new solutions to cosmic problems. We can use them for solving tasks right now, much like sort of shown on the left here. So my last slide here, ArtIMis is a feeder mission into Genesis. That was always our intention. The lab made this investment in this a couple years ago. I believe from my discussions with other labs, we're the only lab that decided to make this large investment in this space, and most of our projects are feeding into Genesis already. Ursa looks like it's the main agentic framework that will be part of the Genesis mission platform. It won't even be called Ursa. We're all dissolving away all these ideas into holistic, kumbaya team in Genesis. But our stuff is a major player in that. As Anna was mentioning earlier, I didn't actually show anything like this, but all of our work uses MCP on the back end. What I actually believe we're going to see in the Genesis mission is essentially massive collections of MCP endpoints that are being controlled agentically. So things like Ursa will be calling into these MCP endpoints, and those endpoints are going to be serving data or foundation models from around the nation at least. So we've been leveraging frontier industry reasoning models. We've been building an AI ecosystem of reasoning agents powering non-language science foundation models. We've got partnerships with industry and academia and dozens of papers. As you can tell, I was very high level on this talk. We could dive into many of these topics and get deeper into the science behind all of them. And we've got deep applications to LANL mission, which is of course very important to us. Mission's actually in our name here. And we're feeding directly into the Genesis mission project. And with that, I want to thank you guys for having me here and having me back.
Thank you very much.
I can answer questions.